Is Gabrielle recording? Yes, okay. All right, well, good morning, good day, good afternoon, good night, everybody. Today, it's my great pleasure to introduce our speaker, Jean-Pierre Eckmann. Professor Eckmann received his PhD from the University of Geneva in 1970, where he studied under the supervision of Marcel Gunin. He's the author of more than 200 scientific papers and has done pioneering work on ergodic theory, period doubling bifurcations, statistical mechanics, partial differential equations, graph theory, and more recently, mathematical biology. Professor Eckmann has supervised 22 PhD students, including one Fields medalist. And since this is a seminar about computers and mathematics, I'll also mention he's the PhD supervisor of Hans Koch, who everyone in this audience knows very well as one of the pillars of the computer-assisted proof community. Professor Eckmann is a member of the Academia Europa, the Göttingen Academy of Sciences and Humanities, and is a fellow of the American Mathematical Society. Presently, he's a retired professor of physics and mathematics at the University of Geneva. Now, his work on computer-assisted proof of the Feigenbaum conjectures, which he'll talk about today, is one of the defining moments in the use of computer-assisted methods of proof and changed the way that we interact with computers in dynamical systems theory and nonlinear analysis. So without any further delay, I'm very pleased to hand things over to
say something so I can check my sound.
Okay, thank you. Can everybody hear me? I hope so. Okay, thank you for letting me talk here. I want to sort of explain a little bit what we did at the time. Now, my biggest worry is that probably half the audience wasn't born when we did this work, and so maybe some things are new and some things are not new. You will find out yourself. So I first will explain what the Feigenbaum conjectures are, then I will sketch how we did it at the time, and then I make a few historical remarks. Okay, so all this started around 1984 or so. There were several studies we did together, in particular also with Hans Koch, who certainly will talk at your conference also. And with Peter Wittwer, whose PhD was on such a proof. We also, I'll explain that we also had to do some sort of pre-compiler that was done with Sylvie Campos and Andreas Malaspinos. And of course, it goes without saying that really the whole thing was initiated by Oscar Lanford. So let me show a few slides about what this Feigenbaum conjecture is. For those who already know, that you can read the newspaper in the meantime or do something like that. So it starts from the idea that you have a one-dimensional map. Mu is a parameter and x is a coordinate, and then mu can vary in 0 and to 2. And under this condition, if x is in -1, 1, then it's mapped by f mu of x again to -1, 1. And then what people did at the time, and still do, is that you iterate this function. So the nth iterate is f acting on the n-1st iterate, and also the 0th iterate is just the identity. And then one sees this bifurcation diagram where so the mu axis is horizontal and the x-axis is vertical. And what you do is you start with a random initial value of x and you iterate maybe 10,000 times, and then you plot number 10,001 to 10,050 or to 10,100. And then you see this beautiful figure, which everybody probably has seen before. Now, the Feigenbaum conjecture has to do with the points which I mark here. So I choose that value of mu where these 2 points happen to hit the 0. This is x equals 0. And then there is another value of mu down here. So this is period 2, and this is period 1, 2, 3, 4, not in this order. And then it gets a little too small for my representation, but here is a period 8, and then 16, and so on. And the mu value where all this accumulates happens to be 1.4055. And the way these blue strips accumulate is exponential at a rate which is this famous Feigenbaum constant here, delta equals 4.66. This number, as far as known, doesn't have a nice formula. It's not the square root of something or the root of an equation. And what is more astonishing, and which was really revolutionary, is that this constant delta does not depend on the family. So for example, instead of taking f of mu equals 1 minus mu x squared, you could take f of mu is equal cosine mu x, and you would get the same delta. So now there is another scale which will come in later, which is the vertical size of these things. So if this is size 1, oh no, I should change that. If this is size 1, then this one is size lambda. And lambda is about a quarter. Okay, and then this is lambda squared. Okay, so there are two constants which need to be explained somehow. One is this delta, and the other is this lambda. And the question is, how does one explain this? So this is explained, as Feigenbaum discovered, through what he calls what is a fixed point equation. I'll show it on the next slide. And it is the organizing center of this phenomenon. The fixed point function is a very complicated thing, and we need to understand a little bit about it before we can go to the computer-assisted proof. So the fixed point equation is this equation. You are looking for a phi such that r of phi, which is given by this long expression, is equal to phi. Now, let me make a few remarks, maybe for those who have seen this before. Many authors write here lambda, and here also lambda, instead of phi of 1. So phi of 1 is equal to lambda, but lambda really depends on phi. Now, what makes this thing a good candidate for something computer-assisted is that this equation is not local. Namely, in order to compute this at x, you need to compute this at lambda x, phi at lambda x, right? Because phi 1 is lambda. And so what you see is that this relates 2 points which are not together, right? In this sense, this kind of problem is different from the differential equations many of you treat, because you have to somehow glue these joint regions together. Clearly, the solution phi star of this equation star, which I will write whenever I need it, must be a complicated function. But it only depends on even powers of x. I'm not going into this. And furthermore, and this will save us, it's a little bit analytic near x equals 0. So this is a drawing which Henri Epstein and Jean Lascaux made at the time. This is the positive quadrant in the complex plane. So here are the positive x, and here is the imaginary x, and the domain of analyticity of this function phi, this is the domain of analyticity of the function phi, is this region you see here below, but it extends into these arms, right? I hope it's more or less clear. And in more technical terms, this is a a domain through which you cannot continue the function outside of this domain. And for those who are really interested in mathematics, the fixed point function acting on this domain is actually all of the complex plane. So you have a small domain here, but the image of this domain under the function phi is everything. And what is even more counterintuitive is that the boundary of this domain is mapped 1 over lambda is about, I forgot, 4 or 2.5 or whatever. So you map this out and still it maps the boundary onto the boundary. If this is not yet bad enough, I show you another representation also made by Henri Epstein and Jean Lascaux. In fact, the real domain, it's very difficult to compute it. And I tried now and it didn't work well. All these red curves are in the domain. And that's why the domain actually covers the whole, the image of the domain covers the whole thing. So I'm only saying this to tell you that after all, phi is not just a very nice function. It's very nice near the real axis. It's real analytic up to infinity. It's also analytic on the imaginary axis. But for the rest, it's quite messy. So you don't expect too much of it. However, what will be very crucial is that there is a domain here, which is sort of a little disk or something like that, where it is analytic. And we will have to exploit this in particular because the equation connects to another part of the domain. So now let's see, here I write again this equation. And I now want to explain something else, namely that we are not only interested in the solution phi star of this equation star, which is actually unique if you normalize the function such that phi star of 0 is equal to 1. Otherwise, you can scale everything. So now what happens is the map R, which is a map in the infinite dimensional space of all functions phi, has a derivative which I call dr, and this is a linear map in an infinite dimensional space, and it has an unstable eigenvalue which turns out to be this famous constant of Feigenbaum, namely this 4.6. Now, one thing which worried us a lot at the time is that this derivative, you really have to apply the chain rule to this expression here. And so there are really 4 terms which need to be differentiated. This phi, phi plus delta phi, it's a Frechet derivative. This one, and this one. So the linear operator is a little bit messy because it has many terms. Okay, so now finally I consider the map family of maps as before, as you know, and look at these mu n's. These were these blue vertical strips which I showed on the first slide. They accumulate exponentially. One way to write this is to say, well, mu n minus mu infinity divided by mu n minus n plus 1 minus mu infinity is equal to delta, which is this 4.66. Okay. So finally, I need to explain how people see the global picture of this thing. So this is the space, this picture is the space of the Banach space of all functions phi, and in this Banach space there is a stable manifold and a non-stable manifold. So under the action of R here, this flows, it's discrete, it flows towards this fixed point. Okay, and this vertical manifold, which is actually one-dimensional, is unstable like this. Okay. Now I also drew here on the side the family mu gives 1 minus mu x. So that's a one parameter family of functions in this Banach space. And as I will show later, or I will mention, this one parameter function traverses this stable manifold somewhere, right? And somehow we have to connect what is known about this region here with what is claimed about the exponential approach of the mu n's to mu infinity. But the point, the point will be that this unstable direction has an unstable eigenvalue, which is this famous delta. Okay, are there questions at this point? Is everybody reading the newspaper, or everybody understands?
Jean-Pierre, I have a cultural question about...
Pardon? I can't hear well. Yes?
Sorry, okay, so I need to raise my voice, sorry. I have a cultural question about the name of the conjecture, because you name it the Feigenbaum conjecture. Wouldn't it be more, let's say, honest or realistic to call it the Cooley-Tresser?
Yeah, this. I mean, I'm not a historian of science. I would call it the Feigenbaum equation. It's not clear who was first. I don't know. You can call it what you want.
Oh, I mean, I don't want to come. I just want to make. I've been spanked during my thesis defense, because by closely related people to Cooley and Tresser, that they should be called Cooley-Tresser instead of Feigenbaum. They done a note without proof, without, let's say, the proof was not, let's say, it could be that Feigenbaum.
Yeah, I know the paper. I don't know. I just don't know. Okay, I can add it, but I don't know how to write on this screen. I mean, maybe.
No, don't worry, don't worry.
Okay, other questions? Okay, so now, now I come to the proofs. So there are several proofs. Many are computer assisted, but I also like the brain assisted proofs of the existence of phi star, which solves the equation star. Now I want to, because this is what I was asked, I want to give some details of the proof of Wittwer and myself, which we did in 1986, in which we proved star and double star. This is star and this is double star, and I note here the uni thing. I think there are now quite good proofs of star. I'm not sure that really there exists a non-computer assisted proof of double star, for reasons I will explain later. Okay, this is a proof. Now, I'm sorry that I don't know exactly what this audience knows or what is obvious for this audience. So please excuse me if I say things which everybody in the audience knows. So this is an example of how to do a computer-assisted proof in an infinite dimensional space. I find the details a little bit boring, but there are a few principles which are certainly of general interest, and I want to more insist on them. The first is, how do you do computer-assisted proofs in Banach spaces of analytic functions? Namely, it's looking for the fixed point of R. Then how does one really define tangent maps to nonlinear maps in function space that shows that dr exists? And then finally, how, and this is the part for which I don't know a non-computer assisted proof, how can one follow the unstable manifold of the fixed point and show that it crosses the manifold, which I haven't defined, which is the manifold of those functions for which the second iterate of 0 is 0. This was, I don't want to go back, this was in this, let me draw it perhaps. You see, I drew blue lines through this crossing here. And this was 0, this 0 goes somewhere and then comes back to 0. And then the next one, which was down here, was much smaller, maybe like this. And there are 4 points. And so that defines these mu n's, which I was using before. So now, let me explain. This is the kind of global problem which usually really needs computational help. So here is again the figure I showed you before. But now this thing here, this surface here is really F2. Oh, I can't write with the mouse. F2 of 0 equals 0. Okay, that's so Ws and this sigma here, this manifold here, are codimension 1 manifolds, and this is a dimension 1 manifold, and so it goes hopefully transversally through this surface, and I will show how one shows this. Now, for the historical thing, Pierre Collet and I actually used such a device for the so-called hierarchical model, but in that case, there was no computer-assisted proof, and in this sense, there is no proof. We just showed numerically that the unstable manifold of what is called the critical surface crosses a certain thing in a finite, after a finite number of iterations. So now, how does one actually prove that this thing, the whole picture? So what I really want to prove is not only the manifold, but I want to somehow get in one catch the unstable manifold and the stable manifold. And this is done by an elegant trick which was invented by Wool, Konin, and Sinai. So first of all, since all functions are even, you look at z equals x squared, and then the variable, and you rescale the variable in the unstable direction directly by the known value of delta. I should have written the star below. And so this is a little bit of abuse of notation. What I mean by this notation is that you act with R on the Z part, but you rescale the mu. And so from now on, I will write R2 for this 2-variable version. So we have now, this is what makes the computation a little bit painful. We have now a function which is an analytic in 2 variables. And so you can imagine that there's a lot of coefficients to be handled. So let me now get a little bit more specific. Throughout now, when I explain things, when there are red numbers, these numbers have to be chosen, like in all your computer-assisted proofs, just right. You know, you don't take it too big, don't take it too small. So good choice here is mu less than 1 and z minus 1 less than 2. So it's a little disk around 1 in the complex plane. And we try to find a fixed point now, not of R, but of R2. Now again, there are normalizations, and these are so this is the same. This is the same normalization as I had before, namely that phi of 0 equals 1. But now for all mu, phi of 0 and mu equals 1 should be some number lambda bar, which is not too far away from the right lambda. And then the derivative, this somehow measures the scale, in the mu direction, I normalize that to 1. Okay. All these constants, or maybe I should have put them red. Okay, so now it gets really boring. So sigma is equal to 0.23, which is a little bit bigger than 1 over the real 1 over delta. Lambda is 1 over 2.5, which is close to the Feigenbaum Goulet-Dresser lambda. And epsilon is another small constant, which somehow has to do with what neighborhood of the fixed point I'm going to consider. And now there is a 5-step procedure, which I will explain on the next slide step by step. So you first, since sigma is equal to this, you start with an arbitrary phi, which is not the fixed point, and you define a new mu lambda, namely lambda mu is equal to phi of 1 over delta star times mu. Okay, so given phi, which is an analytic function in 2 variables, I define a new analytic function in 1 variable, lambda of mu. And now I do basically the R operator, namely here is a phi of phi, and then there is a rescaling lambda square mu and divided by lambda of mu. And then there are these sigmas, which are 1 over delta. This is the thing which works. What can I do? So now I determine, so what this means is that you have these functions and you have to, compute with error bounds, of course, all this operation. And then you determine, now you solve an equation, namely you determine a mu0 such that m0, this thing here, evaluated at mu0 and z equals 1 is equal to lambda bar. And then you define tau, which is the derivative. So this is a derivative of an analytic function. And finally, you define this. And then I will explain that we want to show that this thing here is a contraction. And then it has a fixed point. So now let me go again through these 5 steps or 6 steps. So what is really involved when 5 is given? And we look for a fixed point of R2. So let me just say schematically what is involved. So what does it mean to set lambda mu equals phi of sigma bar mu? It means that I'm evaluating an analytic function inside its domain of analyticity. So it's a compactness argument, right? Then here, what is involved? Again, evaluation inside a domain and composition, meaning many, many evaluations, but no new principle. Now, determine mu0 as the solution of this equation, but don't forget, this is an analytic thing. So you have to solve a nonlinear equation. For example, you use some variant of the Newton algorithm. This is what we did and what many of you do. And then you define tau equals the derivative with respect to mu at this point mu0 of the function m0, which I know. What this means in abstract terms is that you compute the derivative of an analytic function inside its domain, and you can do this. Now, I don't know whether this is probably known to everybody in this audience. And then, as I said, there is this little epsilon, which is 0.005, and this, I have to turn the screen on again. Yes, good. So then you do this evaluation, and with this little stretching, and then finally you just use a fixed point theorem. M is a contraction of a small ball, and therefore it has a locally unique solution phi star. In the meantime, people proved that actually phi star is a global unique solution, and so no, actually what they proved, what Sullivan proved, is that if you know that you have a local unique solution, then it's globally unique. That's the theorem. Okay, so now I want to, before I do, I still have time, yeah, sure. Before I go to the historical remarks, I want to at least, maybe this is overkill, explain maybe the two most fun aspects. So I want to work in the number field, the core of analytic functions, and I want to explain differentiation of analytic functions. And I have to say, this is, these are compactness arguments. I'm a fan of constructive analysis in general, and I still find that Eric Bishop's book, Foundations of Constructive Analysis, is sort of the most helpful book for an analyst to read. It has been re-edited much later again. So I want to explain these analytic functions here, but only in one variable. So in two variables, it's just more of these complicated things. So I imagine that I have some function, some analytic function whose coefficients are fi, and the fi's, I assume they're real. Now the question is, how do you represent f on a computer with rigorous bounds? And the choice we took at the time is that we had two, there's first a power series. So for our purpose, the degree 16 was enough. I told you these numbers here are just best choices, right? So this is 16, maybe. Okay. Now what's new, or what is a little special here, let me do it like this. There is this EL and EH. So EH is sort of a number times something of which I know that it's of at least of degree 17. But EL is some terms where I don't know which order they have. And while it seems unnecessary, somehow this was convenient at the time to have two error terms and not only the more obvious one, namely the higher order term. So this probably anybody would have done. So now, EH is a bound on higher order terms, so it's something like a bound on the sum of all Fourier coefficients, of all coefficients from 17 to infinity. And EL is a bound on terms for which the degree is not known. This comes when you do certain derivatives and you substitute certain things into certain other things, and then you only know it's small, but you don't know its order. Once you've taken this decision here, then everything is sort of obvious, but painful. So what you really do, and this is quite common now, is that the data structure for F is the 17 coefficients, then EL and EH. And what I mean by this is that the FI are certified intervals and EL and H are certified upper bounds. Now, here is a historical remark that at the time, because Lanford knew William Kahan, we knew about the IEEE 7454 standard somewhat before it was published. And so we used it. It can be used in the Intel computer of the time, which are the I080, and the Motorola, which was at the time the 6800 something. As you know, for those of you who use this device, you destroy the pipelines, and so the computation time gets longer because after each operation, if you switch from up to down rounding, you lose time. So many people, for example, Hans Koch, use instead multiplication or things like that, which don't destroy the pipeline. So, for example, if I restrict f to beta equals 1, then I have to do f beta is equal f0 plus beta f1 plus beta to the power 16 f16 plus you don't touch this lower bound term, and then the power 17 of the higher order term, right? And this will give certified bounds. I hope, is this clear? Seems, or not. I mean, yeah. Okay, another important case for us was differentiation, and this just uses Cauchy's theorem. Whenever we do a differentiation, we check where f is analytic. That's a compactness argument. It's basically a compactness argument. So if if a function is analytic in z less than 1, and I assume beta is less than 1, strictly less than 1, then f prime is equal to this integral. And since on the contour the distance is always bigger than 1 minus beta, you can of course bound f prime of beta z by such a device. I forgot here a comma. And so f of beta something has the coefficients f1, 2 beta, 2 beta. And the higher order terms can be bounded, it's the sup over k equals bigger than 17 in our case of k times beta to the k. Many other ideas of this thing can be used. And actually, if you check, the sup is quickly reached when beta is not too close to 1, which was the case in our calculations. So these are sort of the tools. Now, I think this is it. Now I come to the fact, how does one show that the manifold of sigma equals it? So this manifold here, the superstable periods, as it's called, is crossed transversally by the unstable manifold of the, so why is this traversal here? This one, this, why do I traverse here transversally? Right? Because if I were tangential to it, then the result would not be. So what one does, and this is typical of these computer-assisted proofs, I have this map R5, R2. So you check first numerically that if you start at mu equals this fancy number here, and or at mu at this fancy number here, and you iterate 5 times, then the value at 1, which is what counts, is below the surface for this initial value, and it's above the surface for this initial value. And you also check that it's never 0 for mu inside this interval. So what you do is you start with, maybe I should take another color here. You start with a little interval here. It's maybe not so visible. Then you iterate once, and it gets bigger, and then you iterate twice, and it gets bigger, and then it 4 times, and it gets bigger. And at the end, you iterate 5 times, and you have crossed the manifold. That's how you show transversality, right? So, of course, as you do these 5 iterations of this complicated R2, the errors grow, but they grow little enough for the whole thing to work. Okay, I think this ends my, okay. So next question session. Are there any?
How do you check the not equal to 0 for all mu condition?
Yeah, I don't remember.
No, that's fine.
Yes. Yes. No, maybe if I can go back, yes. Basically, I guess we just check that the derivative, you see, no, it's the derivative which is not 0. It's not the value which is not 0.
Ah, okay. Sorry.
Yeah, I'm sorry. Yeah. So if the derivative is not 0, you cross, right? I'm sorry. Yeah, you agree, right?
Yeah, I agree. No, I didn't see that.
No, I didn't see it either. That's the point. Yes. Are there other questions? You know, this technique must also be used many times. So now, if there are no more questions, I will use the remaining few minutes for a few historical remarks, which are, you know. So as I said, most of you were not born when we did this, so some problems of the time are not here anymore. So several problems appeared, which today are practically in existence, but which made our work at the time much more painful. So the first remark is, you know, that computers, if my estimate is correct, were about 10,000 times slower than today. So even if our computation even took an hour today, you would do it in a few seconds. The other big problem is the memory. So you see, we used, so each interval has 2 values, and then we have polynomials of degree 16 in 2 variables. And so there were several, you know, 100 variables. You had to be sort of careful not to use too many variables. These were sort of the problems of the time. This is, of course, no issue at all. Now, a more serious issue at the time, or maybe not more serious, but also serious, is that good compilers were rare and not accessible on all platforms. Actually, I don't remember on which platform we did this. So we had to work with Fortran, which is not typed, and Pascal. C didn't existed, but wasn't so well developed at the time. So what this meant, and this is what I mentioned in the very beginning, is that overloading symbols, which of course, you know, you want star to mean multiplication of 2 analytic functions, or plus addition, or minus, or division, was not possible. So what we did, this was with Sylvie Campos and with Andreas Malaspinos, we wrote a pre-compiler which converted these abbreviated things to Pascal. You can ask Hans Koch, I mean, he at the time wanted to use ADA, but it was also, there were no compilers, so we stuck with these other things. So then the type of data, like in old Fortran, was defined by the first letter of a computer variable, like P is a polynomial and A is an analytic function, and so on. Okay, now comes the worst problem, which ends my talk. Although the programs were documented in detail, they are extremely difficult to read. And I have to say, I found out only now how difficult they are to read. And, you know, it's just a lot of paper you have to read. So it's clear that if anybody would do it now, it would probably be 10 times shorter. So I think that's all I wanted to say. Thank you.
Thank you very much. the wonderful talk. So we have plenty of time for more questions or comments or discussion.
Nobody? Come on.
Well, can I ask then? Yeah. Hi, Jean-Pierre. So I missed. Did you use lambda lemma then to finish the proof of the that the particular quadratic family gives Feigenbaum ratios
What is the lambda lemma?
of Pallis?
Pardon?
The Pallis lambda lemma.
Yes. Now, so the history, yeah, so the history of that was that, you know, Golle, Landford, and I, we did a proof for not this quadratic family, but the quadratic family which had another singularity at the top, namely x, I can't write very well, to the 1 plus epsilon. Now, it turns out that in this case, you can do a brain-assisted proof. And what we did there is we reproved, or we proved something which then turned out to be the lambda lemma, right? But what you are asking, if I can go back to the, yeah, here.
Yeah.
What you are asking is, for example, okay, let me explain to the audience. This drawing is somehow misleading. This surface here is in no way parallel to this surface, and both surfaces are not planes. I mean, they are what they are. So what we did and what shows the proof is that if you know all these things, then the pre-images under R, I can't write this, the pre-images accumulate in a nice way onto WS. That's, I think, what's called the lambda lemma, right?
Yeah, or you can go the other way. Take the forward images of the quadratic family, and they will accumulate onto WU.
You see, no, I think, you see, we don't know, we don't, you know, the delta only appears, let me change the color. The delta only appears in the neighborhood of this. So you have to somehow pull back these intersections. The first intersections are not scaled by delta, but asymptotically they are. So you have to know that this thing is. Now, some people do it this way, right? They take this curve and they map it. This curve, because there was this attraction, is mapped towards this curve. Right? And then what people do is that's called the scaling limit. In fact, we did all these things already with Pierre Golle in the hierarchical model, which is more like statistical mechanics. Other questions?
Yeah, let's see. Can you hear me?
Yes.
Okay, so you're not actually proving that the quadratic family is attracted to it, right? You just basically work along the unstable manifold.
Yes.
Okay. Yeah.
Yes.
By
We
the
could
way,
have, you know, I mean, we could have shown that the quadratic family is attracted to it.
yeah.
You know, also by taking R2 to the 5, and then probably it's already very close. But we didn't do it. So if anybody feels like doing this again, then you can ask this.
No, because I'm trying to do something similar for the almost Mathieu renormalization thing. So there is an analog of the quadratic family there that But yeah, I suppose it's known, right? Maybe by brain-assisted proof that the quadratic family converges to the unstable manifold.
Not sure.
No.
No, I forgot. I mean, some people, what's for example not clear from is that the quadratic family looks like it looks, namely that in this very first slide where you have this bifurcation diagram, that it's traversed monotonously. That's not known. That's known by a brain-assisted proof. I think Misurevich did that. I'm not sure.
What's kind of the negative Schwarzschild derivative stuff that enters?
No, it's more clever than that. Yes. No, I don't remember. You know, for you it's not so long ago, but for me it's. I mean, did Hans tell this audience the other brain, computer-assisted proofs he or we did?
I think Gianni was here a little while ago. He did something. I could do something.
Yeah, I think so.
But I had classes during,
this is the advantage of being retired.
Oh, I can't wait. No.
Yeah, but the problem, I don't get any grants and I won't get tenure. That's the problem. Anyway, other questions?
So, yeah, I had a question on your delta. So further back in the slide,
yes,
in the scheme, you started with sigma being 1 over delta, right? Or
not quite. No. Sigma, this sigma bar, what we took is something about which we knew that it's a little bit bigger than what we of course knew delta numerically very well. So we took a number which we know is bigger than the delta.
And so this,
I forgot why exactly this was useful, but I think it's when you iterate here this thing, you want to be sure that you don't get out, that you have a little bit more of the domain than absolutely necessary. So what you wanted to do here is you would have wanted to take exactly 1 over delta, but since you don't know yet what delta is, you have to take something which is a little bigger. Does that answer this question?
I see. So this delta star is what so the delta star.
The delta star is the official constant. I have a notation mess. I should have called it delta star from the very beginning, and the star up and the star down is the same.
And that star up and star down is the 4.66, that number?
The true yes, which is known to, I don't know how well it's known. Hans computed it with rigorous bounds to, let's say, 20 digits.
And is it, so this is sort of related to my question about delta star. I mean, so using, say, computable and, like Bishop's methods, so you can compute delta star as far out as you want? Or?
In principle, yes.
In principle, yeah, okay.
Yes, but okay, all this, this is also a new, depends what you want. What we did at the time was so-called double precision, not more, because it was already slow enough today, you know, with these packages for infinite precision, I guess you can compute it as well as you want. It's just not known. I mean, here are a few open problems which I discussed with Hans. One question is, which is still open, I think. If anybody, this is a good open problem. Where is it? No. Yeah, what is the spectrum of dr? This is still not known. I think it's not even known that the spectrum is real.
No, that's the main thing.
Pardon?
Yeah, that's the big question.
That's a big, difficult question. So Hans knows about many. Okay, there is of course delta. Then there are all lambda to the, I'm saying something which is maybe wrong, all lambda to the n, but there are other eigenvalues. And nobody, okay, so for a while we thought that these other eigenvalues are related to the quasi-conformal nature of the fixed point. And, I don't know, but Hans knows them numerically to as much precision as anybody would wish, but there's no clear idea what they are. And it's even not clear that they are real. They look real.
I see.
So this needs probably some other insight on this, on the fixed point equation.
Hans, how many eigenvalues you have in your spectrum? We computed about 100 and they were real, but of course we don't know whether they're all real.
Well, as Jean-Pierre said, there is an infinite sequence of trivial eigenvalues, which is lambda to the n. But then I think this is for n odd, and then for n even, there is another sequence which gets closer and closer to lambda to the n. Already this is kind of a mystery, that the others, the non-trivial ones, are asymptotically pretty much look the same. And I don't know how many I have, not that many, but it seems pretty clear that they're all real. But in a way, it's a very fine, you know, like higher eigenvalues somehow say something about the geometry, and knowing that all of them are real is somehow a very delicate thing, and I have no clue, really, no good idea why this is supposed to be true. There's no, you know, if it were not real, there would be somewhere some rotation in the picture, but I don't know why there is no rotation in this whole picture.
Yeah, but you also had this idea that you know, the lambda to the n can be explained through sort of coordinate transformation. But then didn't you have also the idea that basically some singular coordinate transformations explain the other ones?
Yeah, they don't really, but no, I don't really know. I mean, the other crazy thing is that you know, you can formally take something that's non-analytic that goes like lambda to the n for the even ends, and the crazy thing is that the true eigenfunctions look kind of like those either. So it's some weird thing that I don't understand. But yeah, that's one. By the way, there have been a number of papers that either openly or secretly were investigating this. So there is a paper, I forgot by whom, that looks, there is also the transfer function approach to the whole thing. I forgot the details. So you can make an approximation to the transfer operator for this thing and a piecewise linear one, and then you can prove for this approximation that everything is real. But I tried to make this proof work too, but I couldn't. Actually, Raphael and I were once thinking about this thing a little bit for a while, and you know, that stopped too. So on and off, I had thought about this problem, and I really have not gotten anywhere.
So I'm curious, I mean, you know, you can pitch this problem as being a very deep problem because it's like a, you know, Riemann conjecture or something. Because, you know, you don't have a self-adjoint operator, but you do have real eigenvalues. Or you can say this is a totally boring problem because the eigenvalues are interpolated between the real eigenvalues, you know exactly. So what else could happen? So I'm just curious, what is your feeling? Is this an interesting problem, profound problem, or this is just, you know, a nuisance?
Was there a question? I didn't really understand it. But yeah, I suspect it's a really difficult problem. I mean, I know it's difficult, at least for me, but yeah.
You know, Predrag, look, I mean, is it important to know all finite groups?
Yes.
Why?
It's an amazing human achievement. You know, I believe in beauty of mathematics. Yeah.
So this will be less amazing, but, you know, I'm still hoping that somebody comes and say, look, of course, these eigenvalues are such and such. That would be nice, right? Look, half of them are really well understood, right? They're related to coordinate transformations, and so, okay. But what about the others? Why are they there? I don't know. I think, you know, are you already retired?
No, I'm still laboring.
Yeah, okay.
Online. You can follow my mathematical physics course. It's all online, Jean-Pierre.
Okay. Good. I
You will
don't know.
disapprove profoundly, but go ahead.
I don't know what interesting means, you know.
No, but, you know, Riemann hypothesis you find interesting. No? So it's a very fruitful hypothesis of similar nature.
Good. Yeah.
This might be just not.
I still would be happy if somebody comes and say, look, it's just such and such.
Yeah.
Self-adjoint.
If it was self-adjoint, it would be totally amazing if you can do that. That I would find beautiful.
This discussion sort of reminds me of, there was this conjecture many years ago by Dieter Meyer about reality of spectrum. And then, you know, a few years later, I think Gennady Levin disproved this conjecture. So only for small moduli, all the eigenvalues were real of the transfer operator, but he constructed counterexamples. So I don't know whether you are aware of that, but it sort of reminds me that this can be very tricky.
Right, I am taking over as a chair because Jay has to leave right now. So are there any other questions or remarks?
Alles false, huh?
Yeah, okay, well, I guess this is that was a good 20 minutes of questions. So I think we shouldn't feel ashamed that we put an end to this discussion, this wonderful discussion, in fact. Thank you very much, Jean-Pierre, for a great talk. It was a pleasure to have you as our last speaker of this series of CRM camp seminars. So that was
preferred to be in Montreal, actually.
Yes, of course.
Okay, sorry.
Yes, no, it will. Next time.
Can I just add something? Sorry.
Did you have a question?
No, I just wanted to say something.
Oh, yeah.
So there was on the topic. So there was an alternative approach by Babianko, published on, unfortunately, main papers are in Russian from 1980s to the same problem, where he actually proves the existence of the fixed point, and he actually also studies the spectrum of the derivative, but he doesn't prove that it is real. And what is he's doing? He's using interpolation approach to the period Dublin equation, and it works remarkably well. So what he does, he constructs his function using the values of at the Chebyshev nodes. So basically, his operator is becoming an operator on in linear, real, and dimensional space, and he's just solving in terms of, and he gets so what. He solves a linear equation, and then he gets estimates on how good the approximation is. So, and conversions in this method is faster than in the method that was presented here. So I don't know whether this approach is well known. I don't know whether people tried it to solve another problems concerning this renormalization, but maybe there is something there. This is it.
Okay, yeah, thank you. Could you write the name that you mentioned? Pedrag asked about it, and I think it's a good point. The name of the title of the paper in the chat.
Well, yeah, the bagels. Sorry. Yeah, I can write it in the chat. I have just recently, like several months ago, discovered it myself. So the name is Babianko, and his co-author is Yuriev, and second best to Brooklyn. Sorry. Yeah. So yes. So in fact, Frederick is here. So Mark Policott was giving a talk the other day, and
it was beautiful.
What?
It was a beautiful talk. I really loved it. Yeah.
Yeah, and it was joint work with me, but for some reason, I think it decided that it was joint work with Oliver. So Mark me forwarded your email, and I still haven't in mind to reply. Sorry, I haven't done it. So yeah, but I will. It's still. I will try to get to it as soon as possible.
Okay, thanks a lot.
On Chebyshev expansion is. Oh. Chebyshev expansion, as you know, is a good idea for functions where you want a domain of analyticity that's inside an ellipse, and that can be good if rather than a disk. So for a circle map for renormalization, for example, it's a good idea to do a Chebyshev expansion.
Well, whether it's a good idea is always proved by the result. So I'm skeptical. You prove something that I couldn't, and then I take the Chebyshevs. But my experience with this is that it's not quite as simple.
Okay.
Chebyshev is like the thing you take when you don't really know what to do. And so we tried once a circle problem with Chebyshev, and it was very frustrating and didn't work. So
okay.
So basically, if there is nothing natural, I mean, the best thing is to take something natural, and Chebyshev is hardly ever natural, as far as I'm concerned.
Well, I don't see that it's any less natural than Taylor series.
Well, it depends on the domain. If your domain is an ellipse, then there's not just Chebyshev, there is a zillion others. But if the domain is a circle, then power series is certainly a good idea.
Yes, of course.
You know, there's lots of these well-known polynomials that have actually ellipse domain, not just Chebyshev. So Legendre, for example, or whatever.
Okay. Well, bye for now.
Okay, yeah. So yeah,
Bye,
that's a good point to
everybody.
stop.
Thanks.
And thanks a lot, everyone. And we will start again the CRM camp seminars in the winter. So we'll keep in touch. So thank you very much again, Jean-Pierre, for the wonderful talk.
Okay.
Thank you. Bye.
Bye-bye.
Thank you.
Thank you.
Bye, Jean-Pierre.
Oh, there's lots of people, yeah.